This is part 5 of the AQA topic, amount of substance. In this section, we're going to be looking at titrations and titration calculations. I think it's really important actually to note that we're not going to look at the practical aspect of titrations, thinking about the things that would come up in the practical paper 3. That will be discussed elsewhere. We're going to focus predominantly on how you carry out the calculations. As always, I'm going to recommend that you pause, try each question, and then review your answer and see if you're on the right lines. So to start with, I'm going to show a general step-by-step guide to carry out a titration calculation. And if you've watched the previous videos in this series for amount of substance, you'll recognise some similarities. We've got this table where we've used a very similar one for empirical formula, and we've used an even more similar one with reacting masses questions that we looked at in part 4. In this, the difference that we have from reacting masses is that we have concentration and volume and moles rather than mass, molecular mass and moles. Once you take that on board and you realise we're just using the other mole calculation, it becomes quite straightforward. The mole ratio here is worked out in the same way as reacting masses. You simply look at the balancing of the equation. So with all of this in mind, I'm going to move on, have a look at a couple of examples of titration calculations, and then we're ready to move on. So here's the first question. And in the first instance, we're asked to calculate the concentration of the sodium carbonate standard solution. So we were told that we've got 2.65 grams of sodium carbonate. We've added it to a volumetric flask and made it up to 250 centimetre cubed. Now, if I want concentration in moles per decimetre cubed, I first need to work out moles. So I take my 2.65 grams, I divide by the MR, which is 106, and I get 0.0236 moles. I've now got my N, I want my C, so I'm going to need my V. And we're told that we're making 250 centimetres cubed. So when I do C is N over V, I'm going to remember to convert my CM cubed into DM cubed. That's really important because concentration is in moles per decimetre cubed, so this should be in decimetre cubed. And that allows me to get to a concentration of 0.094 mole dm to the minus 3. We've then got some balancing of the equation, so we know that we're taking sodium carbonate and reacting with nitric acid, and you have got to bring some chemistry knowledge with you here to realise that a metal carbonate and an acid makes a salt, water and carbon dioxide. Once you've got all of that in place, you can simply balance it, and that's what we have here. And that then allows us to do the titration calculation at the end. So I draw out my table, I've got my species I know and my species I want to know, I have my CVN ratio, and I can put my concentration in that I've just calculated, 0.094. I can take my volume. Be really careful here because we may have made 250 centimetre cubed, but we're only actually using a 25 centimetre cubed sample. So that's about reading the question carefully. Once I've got those two, I can calculate my moles as 0.00235. My mole ratio of sodium carbonate to nitric acid is 1 to 2. We can see that because there's 1 mole of sodium carbonate and 2 moles of nitric acid. And if 1 mole reacts with 2 moles, 0.00235 moles will react with 0.0047. We're simply carrying that ratio forward. I then have my volume that was provided, the average titer of 26.7 cm cubed. Again, remembering to convert that to decimetre cubed. That then allows me to work out my concentration, and I get 0.176 mole dm to the minus 3. Another question for you to try here. So this is probably one of the more straightforward titration calculations. The equation is relatively simple. We know that an acid plus an alkali makes a salt and water. When you actually look at all of this, it's fully balanced, so we don't need to do any more with it. That means we can go on to build the table. And what I'm going to do here is follow the table through in a slightly different way, because different people prefer to approach this in different ways. So I'm going to put in every bit of information at my disposal. And you can see that I've got my concentration of HCl, I've got both of my volumes, and I've got my mole ratio. Now, the advantage of this method is you can now start to pick out which bits you don't know, but how you can work them out. For example, we have a C and we have a V, so we can work out the N, and that comes to 0.0025 moles. If I know my ratio is 1 to 1, my ratio is therefore 0.0025 to 0.0025. I've then got my N and my V, so I can work out my C, and it comes out as 0.083 mole dm to the minus 3. Next question to try here. Okay, let's take a look at the equation. So in this case, it's an acid and an alkali again. H2SO4 plus KOH goes to K2SO4 and H2O, but there is some balancing needed here because we've actually got 2 Ks on the right and only 1 on the left. That then means the hydrogens need to be balanced and the oxygens, so we've got a 2 on the H2O as well. And it does ask for state symbols here, so let's add those in. Aqueous, aqueous, aqueous. Remember, water will never be aqueous. It will be liquid because it's not dissolved in water. I can then build my table. I can substitute all of the information in that I have been provided with. I can see I've got a C and a V, which allows me to work out my N for KOH. I can use my mole ratio, 2 to 1, so I'm going to halve that 0.0035, and I get 0.00175. I've now got an N and a V to calculate my C as 0.07 mole dm to the minus 3. So that brings me to the end of the video walkthrough for titrations. I have to say, by far the most effective means of tackling titrations is, once you're equipped with the key facts and you're confident with them, going on to past paper questions and working through them until you can confidently apply that knowledge. Thank you for listening. Goodbye.